let's jump right in. And to get started, I thought I'd kind of walk through a funny exchange I saw on Twitter recently. It starts pretty innocently. Someone just asks one of these language models, I think this is Bard from Google, to give an example of a JSON dictionary, and they crucially say don't include any text before or after the JSON, right? Simple enough, but of course the model doesn't quite follow this instruction and puts a bunch of preamble text in there. No big deal. We know how to change this, so let's be a little bit more descriptive and give it an example and give it clear instructions of things we shouldn't say, right? And again, the model chips out this chipper, sure, here's an example of a JSON dictionary. So then you get this kind of frustration mounting. You start writing these long paragraphs of descriptions of instructions and even result to some really kind of desperate text. I'll let you read it on the slide if you want, but at this point, this developer is saying if you don't include any non-JSON text in your answer, even a single character, a real human being with a family that loves them is gonna die. And just really, my favorite line here is you can't undo death, Bard. But despite, that's what it takes to get these models to do what you want sometimes. So it works, but we don't think that's the best way of doing things necessarily, right? And I think many of you, judging from the reactions popping up in the chat, think that this is like probably feels familiar. I'm sure many of you have dealt with this with ChatGPT or other language models you're playing with. And we think so too. And that's why we created guidance. So this is a new way to think about interacting with language models, a new programming paradigm to help models behave the first time around. And what do we mean by this kind of new programming paradigm? Well, as we saw earlier, the traditional experience of working with language models is just text in and text out. The model does whatever it wants, and you have no kind of guarantees on how this process works. You just have this text to play with. But with guidance, we think of this as language model programming. Instead of writing these plain text prompts, we get to write, as software engineers, rich, expressive programs. And guidance sits directly in the inference stack of the model, which for the first time makes it truly possible to control these models in ways that you can't do with the traditional text and text out interface. And we'll go into a lot more detail about what I mean by this and how it works throughout the course of this stack. When you do this, when you kind of rethink how these language model interactions work, you get all kinds of benefits. You get significantly more control, higher quality outputs, and then, as Alex alluded to earlier, both faster execution and lower cost. And we're not just talking a little bit faster, like 2% here or there. Sometimes we can see significant improvements, like 60 to 70% faster execution and reduction in kind of cost to you in running these prompts. So we'll get into details about that too. So, okay, let's start by talking about how all this works. I made a lot of empty promises. Let's hopefully convince you that we can kind of meet all of them. Right now, there's a couple different paradigms people use to interact and build on top of language models. And the first one is fine-tuning, right? But I'm not going to spend a lot of time talking about fine-tuning because we all know it has its challenges. You have to collect a bunch of data. You have to be expert at figuring out how to tune your model. Are you doing parameter efficient, full model tuning? There's a lot of complexity in kind of fine-tuning a model. And once you fine-tune a model, it loses its generality sometimes. So you lose its ability to kind of reuse it for other tasks. And when the world changes, you have to re-fine-tune it again and again. So although it works sometimes, it's cost prohibitive and takes a lot of expertise. So we're not really going to talk about it. And what guidance is doing is not fine-tuning. The other kind of paradigm that all of us have been familiar with since the GPT-3 era is prompting, where you don't change the weights of a model. You don't need excessive data. You just get to tell the model what you want to do in natural language. But as we saw with that example earlier, this has its shortcomings too. Door number 3 is kind of where guidance starts to come in. But before we get into that, I want to kind of take a sec to dive into how prompting actually works. And we'll use that to motivate what we're changing in the guidance paradigm. So in order to talk about this, I think it's good to take a very concrete use case. And this is one that we did as a part of a collaboration at Microsoft, where with a customer, we wanted to extract data from doctor's notes and transform that data so that it can work with downstream software, right? So a doctor might write kind of messy, unstructured notes, and we want to kind of pull out rich, precise, structured summaries of that so that we can send patients reminders or autofill events and calendars, things like this. And the standard way of doing this is, of course, to write like a very long prompt. You chuck 2,000 characters of text into a system prompt, and then you tell the model very precisely exactly what you want to see, what tone the language model should take, who the audience is, all this kind of stuff, right? And crucially, these constraints today, when you want the model to follow really specific instructions, are just expressed in text. And there's a lot of open questions, dozens and dozens of research papers written about what is the right way to express this constraint. Should I put Markdown or XML or JSON in the prompt, right? So it's really kind of an inexact science of expression here. And then at the bottom is kind of an example of what one of these notes might look like. So we take this combination of things, this prompt that we write out, these constraints that we chuck in the prompt, and this kind of text that we want to operate over. And by the way, the more that these kind of grow in size, the more our kind of costs and latency grows because of how these language models process this text. But we take all of these, and the goal is to pass it off to a language model and get back something like this beautiful structured JSON output that our enterprise software can take and understand and plug in, right? And so now I want to take just a little bit of time to dive into like, what's going on under the hood when we take these inputs, pass it to a language model, and generate this output. So, many of you probably know all of these details, but like I think it's just worth level setting for a little bit. So give me some rope here as we go through this kind of exposition. All right, so for simplicity, I'm just using this little neural net icon to represent all language models, but you should know that every language model works the same way, essentially, whether it's an OpenAI giant GPT-4 or the baby Phi 3 models, all of them kind of follow the same fundamental notions. And the first thing to understand is, of course, that language models generate text not all at once, but one token at a time. And a token is just kind of a collection of characters, anywhere between 1 and sometimes as many as 20 characters, but it's almost like the alphabet that language models reason over. Uh, and LLMs think in tokens, not text, so you can see these kind of colored highlights here representing the token space of the output. And when generation happens, it's not generating just a giant blob at once, you're getting kind of one token at a time. And the way this works is around this fundamental property of next token probability calculation. So it's really just kind of predicting the next token. The language model takes in everything that's passed in the input, in our case, the prompt, the radiologist notes, and all it's really trying to do by the end of its execution is to calculate what token is most likely to come after all of this input text. So modern LMs have vocabulary sizes of like 100,000. GPT-4o has 200,000 tokens. So they have these kind of huge option space to choose between what token is likely to follow. And the goal is to build a probability distribution. So the idea is for every single token in the output vocabulary, can the model assign a probability that that specific token follows the text that came before it, right? Really, really simple. But really simple output. But in order to get here, you have to spend a bunch of money on GPUs and do expensive matmuls and, crunch a bunch of numbers on many, many GPU clusters, right? So this is really where some of the expense of using these systems comes in. But once we have a probability distribution, then the LM needs to make a choice and select what tokens comes next. So we build this distribution, and then we have to sample from it. And this isn't always the token with the highest probability. So if many of you are probably familiar with this temperature parameter, if you increase the temperature, it kind of determines how much to follow this distribution. So the more you increase your temperature, the more you're kind of ignoring the distribution and sampling randomly. But if we set the temperature to 0, we always pick the most likely token. But sometimes we want a little more creativity, so we bump that number up, right? So there's all kinds of ways to kind of change how the sampling works. But the big intuition is that you build this probability distribution, and then you select a token. And once you select a token, it gets appended to the input. And then we repeat the process over again. So now the model has seen the system prompt, the radiologist notes, and this one curly brace that we selected. And we do the whole operation over again. Calculate these probability distributions on these GPUs, select a token, append it to the input, and repeat, right? And this kind of auto-regressive nature of generating this one token at a time, doing all these operations on GPUs, is exactly how language models produce text. Eventually, we finish this process. We've done this maybe 150, 200 times, and we end up with one of these structured outputs. But here's the problem. How do we know that the language model picked the right token every single time we did this, and the magic of probability sampling? If we miss one comma or one quotation mark or one curly brace, then this JSON is going to be malformed, and we have no way of working with that in our downstream software. So today, what most people do is they pass off their initial prompt, they get a response, they write this validation code, and then they have to check and see if the output was what they expected it to be. And if it was, then they're happy. But if it wasn't, then you probably have to try again, right? And maybe you tweak the prompt or you bump the temperature up or down. But you can get stuck in this kind of iterative retry logic of just getting the model to produce something that's structured. So let's talk about how we can change this. And now we're going to introduce a new notion to you called constrain decoding. And this is where guidance kind of comes in. It's a library that encapsulates these notions of prompting and constrained decoding to fix these types of problems and give AI developers much, much deeper control over what these models are doing. And the best way to kind of think about this, we found, is to just draw an analogy to how the software stack for CPUs has evolved, which is a super well-oiled machine at this point, right? So in the kind of traditional software computing world, we have these wonderful tools like compilers that take high-level code that we get to write in languages like Python, and then kind of automatically turn it into very low-level interactions with the hardware that optimizes things and kind of governs this low-level interaction space that you as a developer don't really need to worry about. We just learned that LMs kind of do the same thing like every time for every token that they generate. So just like a compiler does for CPUs, we wanted to make software that kind of sits at the low level of these language models and optimizes the inference process for you. And the way that you do that with guidance is that you write these programs, not prompts. But I want to be clear, guidance is just a Python library. So you can use everything you know and love about Python to start writing these programs. And we'll talk about this in a lot more detail throughout the talk. But you get to kind of use the best of both worlds. You get to precisely express your constraints in code, because some things are a lot easier to say in code than they are in natural language. And you also get to use the kind of prompting world of expressing some vague concepts in natural language that are hard to express in code. I mean, there's a reason we're using a language model, right? Not just writing old software. So users write these guidance programs that are interleavings of Python code and text, and they get to pick which one is best for each circumstance. On the right side here is how we wrote this kind of radiologist example up as a guidance program. Don't worry about reading the specifics here. We'll go into all these details, but the main idea is just I just wanted to give you some intuition that it is just plain Python code. All right, once we have this, though, we can do all kinds of cool things. And I want to first walk you through these optimizations that we get to do, and then kind of pop back up and talk about how you write these for yourself. So the first optimization we do is called token injection, where we'll completely skip over the LM for some tokens that we know must be in the output. And for those of you familiar with kind of speculative execution on CPUs, this is kind of like that, drawing again to the compiler analogy, but we never make a mistake. And let me tell you about how this works. So the intuition here is that AI developers often know the structure that they want to see in the output, right? And in this case, all of the structure in the JSON is something that we know has to be there. So this is text that I've highlighted in blue here. The keys of the JSON, the quotation marks, the curly braces, all of these are kind of structural tokens that determine whether the JSON is valid and meets our specification or not. If any of these is not correct, then our parser is going to break, our downstream software is going to break. It's something that we just can't afford to get wrong. So the idea here is that why should we even have the language model generate this text when we know it needs to be in the output? And the way guidance works is that it looks at this program that people have, that the guidance user has written, and it notices automatically that the first 17 tokens are completely deterministic, right? There's no point kind of going through that probability generation cycle. So we can just skip over talking to the language model altogether and just directly inject it into the state of the language model. This isn't completely free. Basically, what this means is we have to tokenize the text and update the KV cache. But modern pricing indicates that this costs exactly 1/3 of what generating these texts one by one would have cost. And it's also essentially instantaneous, as opposed to waiting for that text to generate one by one. So you get this kind of speed and quality improvement when you do this, but note that it's also eliminating any possibility for hallucination or errors here, right? These structural tokens are not being generated through probability sampling anymore. We're just inserting them right in. So, I'll walk through a little bit about how this works, but for the first 17 tokens, we inject them into the state, and then we get to a point where we actually need to generate something. Like the ID is not deterministic. And guidance recognizes this, so we do the kind of standard routine, and we generate the one token that represents the ID. And then guidance notices that the next 7 tokens are completely deterministic again, so we get to skip over the LM, inject them into the state, and kind of repeat this process over and over again. And we'll notice that 70% of the output tokens in this JSON generation example are completely skippable. They're just structural tokens. So you get speed ups, quality improvements, and a cost reduction all at once in this use case. I think it's really kind of hard to reason over getting all three at once, right? But it turns out that this kind of paradigm applies to many kind of language modeling tasks. All right, I want to tell you about a couple more low-level things we do. It's not just token injection. And the next one is called masking, where we start manipulating these probability distributions to remove options that don't comply with your specification. Now, this one's a little different. It doesn't save any money or like GPU cycles, but it does increase quality and will guarantee that the model follows your instructions here. So let me tell you a little bit about what I mean by this. The idea is that developers can now say something precisely in code to constrain the model's outputs. They can use arbitrary Python code, regular expressions, anything that kind of feels natural as an expression language. We support regex, context-free grammars, and Python code today. And the idea is that when the developer says, hey, this ID really needs to be a number, we'll go look at that probability distribution after the model has calculated it, and then just start manipulating it and crossing off any option in the token space that doesn't comply with that specification. So, when the dev says it has to be a number, we'll look through these token values. One is a number, so we're good to go. The word ID isn't, and so on and so forth. Remember, though, that the model is still making the choice here. Like the model is still generating the probability distribution. It's still figuring out, what the relative ranking of these things are. We're just preventing bad options from being selected. And once we have these kind of two low-level primitives, we can start to do all kinds of really fun and complex things. So I'll take a little bit of time to walk you through one more of these kind of complex constraints that we have. And we call this one select, and this is one of the most popular things that people use guidance for today. And it's really simple. Sometimes you just want the model to pick between a list of options. Maybe you're doing classification. Maybe your JSON, in this case, needs the model to pick between one of 7 things that are enums in your downstream software. A very common use case. And in this case, in this kind of medical collaboration we did, there was a part of this JSON where there was exactly 7 different values that were allowed to be generated. And now, let's take this constraint that users just get to specify in plain Python. This is just a Python list passed to a select function, and walk through what guidance does under the hood to enforce this and optimize this. So the first thing guidance does is it automatically tokenizes the text. Remember, these language models think in tokens, not in text. So we have to kind of align with the way the language model is processing text. And everything the language model has generated so far is already in the kind of model state input, right? So this is just kind of getting up to the point of generating the region in body. And one kind of immediate optimization is just that all of these options share a prefix token. So every single thing starts with a quotation mark and an angle bracket, and the user has specified that the only thing that's valid is one of these 7 options. So guidance knows that this first token must be in the output. Let's not generate that. We'll just inject it into the state using that token injection that we talked about. Afterwards, we move on to the next set of tokens. And now every one of these is different, but there's only 7 options. And now we can use this masking trick to force the model to pick between one of these 7 options. So at this point, we kind of need the LLM's power and intelligence to actually make a choice, right, between given everything that it's seen before. We can't just kind of use automated software to optimize this. So we'll notice that all of these options are different. And we'll do the usual operator of tapping into the LM on the GPU, generating a probability distribution. And then crucially, we'll just mask out anything that doesn't comply with one of these top 7 tokens. And once we've done that, we can force that the model is going to pick something that aligns with the user specification before. Let's say the model locks in this kind of CHE token. We'll add it back to the input. And apologies, PowerPoint's hanging up a little bit on me. And now we know that when we've locked in the CHE token, we don't need to generate the rest. The only thing that started with CHE in the list of allowed options was the word chest. So we can just inject the rest of the tokens completely, again, skipping over the LM without having to go back through that expensive process of generating text. So what could have taken up to 7 forward passes on the LM, 7 of these autoregressive cycles, we can do in just 1 with this select operator. And again, it's guaranteeing that control for the user too. So it's always guaranteed to give something that the user specifies. There's all kinds of other things that we've built. One of my favorite ones is this one called substring, where we can guarantee that the model writes a quote or any valid subset of existing text that you've passed in. This is particularly useful. Like in this case, the medical kind of collaboration we had wanted a supporting quote for every kind of finding that they extracted. If you're doing citations, summarizations, often it's useful to kind of constrain the model to write something that it's seen before. And we can, in this narrow way, actually completely eliminate quote hallucinations. Now, you have to be a little bit careful here. Just because the model is constrained to write a valid substring doesn't mean it's going to write the right substring, right? So sometimes the model can spit out just the word no or the number 12. All of those are valid substrings of the radiologist note here. You need the model to be competent, and you need to prompt it well to kind of align it to do the right thing. But we will just make sure that it will never kind of go completely off the rails and generate something that isn't a real quote in the text, right? So again, guidance is not going to solve all of your problems, but we think that it kind of fixes part of the software stack and helps solve some key important problems. And there's dozens and dozens of other examples on our GitHub page too. These are just a couple of my favorites. And by the way, when we're doing these kind of extra constraints, we can skip tokens along the way too. So if you start layering in the select optimizations and substring optimizations, suddenly on this medical collaboration we had, we're getting closer to 85% of the tokens skipped from 70%. That one was kind of a private, like Microsoft, proprietary consultation. We wanted to prove that this works outside on a reproducible benchmark too. So we went to LangChain's chat extraction benchmark dataset, which we think is the most popular JSON benchmarking task in open source. And we ran it against 3 different models. And on the far left is when we ran the benchmark exactly as is. So this is very similar to the medical collaboration, but in a publicly open source benchmark dataset. On I'll walk you through really quickly what we did here, and just know that we're going to make the code to reproduce all of this completely available on GitHub. But at the far left, we took three different models, Llama 2, Mistral, and Phi 3, and ran them directly on the benchmark and tried to measure their accuracy. And most of the models did pretty poorly. The benchmark itself just wasn't configured that well for aligning with how these models work. In the middle, we kind of went through all of our prompt engineering and kind of data engineering muscle to try to give the model as much kind of help as we could. So we went through a lot of effort to parse the output, check for substrings, like write all the validation code that we traditionally would do and extract the right thing from the model. Now, this takes a lot of manual effort on our part, but when we do that, you can see that the models start to perform a lot better, right? Particularly Phi 3 starts to do really, really well if you just give it help in kind of extracting the right output format. But the main thing, though, is that if you just run it with guidance, you get 100% accuracy just every time out of the box, right? Like without having to go through all of this manual effort, because we're fundamentally rethinking how we interact with these models. It's not just the text in, text out paradigm anymore. And again, all of this will be completely, available on GitHub. The other cool thing that we can show is kind of the cost reduction side. So we've instrumented all of this in the LangChain benchmark too, and on their suite of many different kind of chat extraction tasks. I'm just putting the numbers for Mistral here, but this holds for Phi and Llama and all the other language models too. You can see that guidance generates this output in about 20% of the time, and uses about 10% of the generated tokens as kind of doing it the traditional way, right? So again, this isn't going to solve all of your problems in all of your scenarios. Structured data is kind of where guidance really shines at. So of course, we're going to see the best kind of numbers here. So I don't want to oversell too much, but there is kind of real utility that we're seeing beyond the kind of Microsoft use cases.